Hey everybody, here is Unit 5, Lesson 1. In this lesson, we're going to talk about radical functions and their graphs. I've written down a space for all of our vocab words with each type of radical function we're going to talk about. The reason we don't have any space for definitions of these words, because we have been over all these words except maybe one or two prior to now. We did it for quadratic functions and their characteristics, as well as cubic functions and their characteristics. So we've seen all these words before in rational functions a couple times. So we're just going to go over as if we already know the words because you do already know the words. If you're struggling to remember what the words mean, feel free to flip back in your journal and check out the pages prior to this in other units where we did go over what all the words were defined as. Up at the top here, it says a blank is any function with an x in the blank. We will be looking at blank root and blank root functions, which are the inverses of quadratic and cubic functions. We will also use previous blank knowledge to find the graphs of transformed functions as well. Before we fill in that, I do want to add right up here, there we go, a radical symbol. So that is a radical. It's also called a root symbol. And then the stuff on the inside is called a radicand. And this number on the outside is called an index. It decides what root we're looking for. If you don't see an index, the invisible index or the implied index is 2. So let's go ahead and fill these in. A radical function is any function with an x in the radicand. So under the root symbol, we will be looking at square root and cube root functions, which are the inverse of quadratic and cubic functions. You might notice if you look at the graphs, they are basically just those functions tipped over. This one obviously only shows half of it because then it would be a function if we showed the other half. And this one you can see really is just like a tipped over cubic function. We will also use previous lesson knowledge to find the graphs of transform functions as well. That is in lesson 2. Perfect. Right up here, I'm going to add our parent function for each one. For square root, it'd be y equals the square root of x. And then for cube root, it would be y equals the cube root of x. Notice for the cube root, we do have that index telling us it is a third root. Notice on square root, we do not have an index. There is an implied 2 here, kind of like there's an implied 1 right there and right here. We just don't have to write them down. Perfect. Let's go through the words. We have intercepts, restricted values, domain and range, asymptotes, starting point, which is our one new word here, extrema, intervals of increasing and decreasing, concavity, and end behavior. So talking about intercepts, the first thing we're talking about here is our x and our y intercepts. I'm going to mark those right here. We have an x-intercept at -4 and a y-intercept at 2. So x-intercept is -4, 0. Y-intercept is 0, 2. Restricted values, remember, are where our graph does not exist. Previously, we've learned it as where the denominator is equal to 0. We don't have a denominator here, it's just 1. So what we're going to focus on is what we couldn't stick in here, and it would make sense. In this case, that would be any negative number. If I put a negative number in here, or a number that makes this negative, I wouldn't be able to exist at that point because you can't take the square root of a negative number and exist. So what we're going to do is identify where our graph is. It goes till here at -4. It does not exist over here. So it exists over here forever until -4 from going backwards there. It doesn't exist this way. So our restricted values, which are x values, is going to be any number that is less than -4 because my graph doesn't exist there. Next is our domain and range. Domain is just asking where does the graph exist, so the exact opposite of restricted values on the x-axis. And range is asking where does the graph exist on the y-axis. So looking at our domain, we're going to go from left to right. The smallest it gets is -4. That does get a bracket because it's a solid dot. And then all the way over here goes to this arrow. That arrow goes on forever towards infinity. Infinities always get parentheses because you can't exist at infinity because it's not a real number. Good. Now trying this way, the farthest down I go is this point here, which compared to the y-axis is at 0. It gets a bracket because it does exist at -4, 0 right there. It's a solid dot. It goes up until this arrow, which is going in the up direction, so it's going towards positive infinity. Again, still gets a parenthesis because it doesn't exist there. Next are asymptotes. Remember, asymptotes are discontinuities within the graph that make the graph veer off towards infinity like this. We don't have any of those for either of our root functions, so we're just going to put none, and that's going to be true for all of them. Okay, next we're going to go over our starting point. Sometimes it's called an ending point. If you were to go this way, if our graph were to flip over, it would be an ending point. But we're going to call it a starting point because for the most part, that's where we're going to start. I'm going to write that there. It is -4, 0. It does happen to be the y-intercept. That is not the x-intercept. Sorry, that's not always true. But this time it is. Next, we have extrema. Remember, extrema are going to be our minimum and our maximum points, minimum being a low point, maximum being a high point. And we're looking for a definitive point where the graph does exist. If you look at our graph, it goes up forever. So it does not have a maximum point because it goes towards infinity. It does have a minimum point right there. Put minimum at, and then normally we're just looking for that y value. So here's our lowest point. It goes towards 0 on the y-axis. Good. Next is our interval of increasing or decreasing. Our graph, since it is so kind of disjointed, has just one part, it's either going to be increasing or decreasing, not both. You're going to have to pick one or the other. So if you look at our graph, we're always going to read from left to right, just like we read a book. And going towards the right is getting higher. So it's going to be increasing. That means it is never decreasing. So I'm just going to put none for that. And it's increasing along its entire domain. So from -4 to infinity. For these increasing and decreasing in concavity intervals, you're always going to use parentheses just because of the nature of the interval. We're not going to use brackets for that. Next is concavity. Just like on the previous one, because of the nature of the shape of this graph, you're only going to have one or the other. So remember we used to call it concave up and concave down. I know it can be a little tricky just because of the shape of these graphs, but you have to think of it as if you were to swoop and continue the graph, right? My graph goes like this, and it would eventually come back down. If my graph was going like this, right, it would eventually come back up. So here, like that, that's obviously concave down. Another way to look at it is if you can stand under the graph like an umbrella, right? This is our little umbrella. Or if you can stand on top of the graph when it's not an umbrella, kind of like a slide. I'll show you that on another one. This is concave down, down, and it's concave down the entire time along that domain, starting at -4 and going towards infinity. And our last piece here is our end behavior. I'm going to give you an L and an R for left and right. Here's the left, here's the right. On the left side, we want to know where the X is approaching while the Y is approaching. Same for the right side. So if I look at the left, it's right here. Along the x-axis, the graph is approaching this point here, which is at -4. Along the y-axis, so looking up and down here, our graph is approaching this point here, which is at 0. On the right end, looking over here, here's our right end. On the right side, the x is going this way. It's approaching that arrow, which is going in the positive direction towards positive infinity. And on the right for the y, it is approaching this arrow, which is kind of going up a little bit. So that's going in the positive direction for infinity as well. And there we go. There are all of our words and things. Go ahead and look at the next page. We're going to try number 1. So go ahead and pause, see if you can get as much of example number 1 as possible, and then come back when you're ready to check. Go ahead and check your box. We might have a slightly different answer for this one. That was just kind of an estimation. That's okay if you're a little different than mine on the 1.2, which is right here. The only thing I think we're probably going to trip up on, because I almost tripped up on it too, is going to be this range right here. Remember, our range in our domain always, well, any interval really, always goes from the least to the greatest amount. The lowest our range goes, which is along the y-axis, is down here at this arrow. If it's an arrow, it's going towards positive or negative infinity. This in case is going down, so it's going to negative infinity. That means we're going to start with our negative infinity, and then we're going to exist up here until we get to 3. And that 3 gets a bracket because it's a solid dot. Everything else I think is generally pretty solid. Maybe restricted values, remember that's where we don't exist. So I looked where my graph does exist. I just looked at the opposite of that. So it exists until -1. It doesn't exist this way in the smaller numbers. Okay, scroll down. Go ahead and pause, try number 3, and then come back when you're ready. Here is our next box. If you want to go ahead and check all your answers there. I realized in the last one I did not go over concavity. I just want to make sure we go over that one more time. So I'm going to come here first. Okay, remember concave up and concave down. Concave down, you can stand under your graph. Or you could also think of it as down like a frown. And it's going to be concave down the entire time. It goes like this. It never like flips back up again. That means it's going to be along the entire domain of -4 to infinity. And the reason that that always has brackets is because all intervals except for domain are going to have, or sorry, always has parentheses, because everything except for domain is going to have, or range is going to have parentheses. The other one that I didn't talk about last time was this one, our min or our max. This one has a minimum point. It goes down to right here. It does not go any farther down than that, and that is at -8. So I put minimum at y equals -8. And then I do want to go over that restricted value one more time. Remember, restricted values are where we don't exist. The graph exists starting here at -4 and goes on forever, so it doesn't exist over here in the numbers that are between -infinity and -4. Perfect. Let's go back and look at our other one. Same process here. We're going to go through all these words here, and then we'll try that practice one. Intercepts, you cannot see the x-intercept on this graph, which actually also happens on the other one. I did it on accident twice. Because the nature of these graphs, they go all the way on the left side towards -infinity and on the right side towards positive infinity along that domain. There is no break in the domain of these graphs. It is all real numbers, meaning it will eventually cross the intercept. It's going to go down forever. And eventually it'll intersect. We just can't see it. I want to say it's around like -60 or something. So we're just going to say x-intercept can't see. And then for the y-intercept, you can see it. It's at 0, 4. So the way we know that we would eventually see it is because we do have an arrow going down towards the axis. That's how you know. For this one, if we didn't see it and we had this, right, we would know there wasn't, let's say it was here. Sorry, that's a bad example. We'd say there wasn't going to be one because this one stops, it doesn't keep going, and this one's going up away from the axis. But this one, it does go towards the axis right there. Restricted values are wherever the domain doesn't exist. This exists from arrow to arrow on the left and right. So there are no restricted values because it exists along the entire domain. So our domain goes from left to right, arrow to arrow. Oh, sorry. There we go. And that means I'm going from negative to positive infinity. Same for the range, actually. On the bottom here, I'm down here. And you might say, oh, you're going towards 3, but I have an arrow. That arrow is going down towards negative infinity. And then here I have this arrow, it's going up towards positive infinity. So my range is also all real numbers or negative to positive infinity. Remember, we said we don't have any asymptotes for any of these. Our center point is the very middle. That is 1, 5. And that's helpful because it'll tell us where we switch our concavity. Extrema means we have a highest or a lowest point. We don't have either of those because it does go on forever, arrow to arrow. So none that's going to be true for all of them. Intervals of increasing or decreasing, starting from left going towards the right is going up. So we are increasing, we are not decreasing. And we're increasing along that entire domain which goes from negative to positive infinity. Concave up and down. Now, this one switches at the center, just like it did when we had cubics. When the cubics looked like this, we also switched at the center. So I'm concave up until right here. You can see I was seeing on top of the graph. And then concave down from here because now the graph is my umbrella. So I'm concave up from negative infinity until that center at 1. And I'm concave down from 1 to forever. And lastly, our end behavior, I'm going to go ahead and mark my LR and then put it on the graph. Left side and the right side. On the left, as X is approaching an arrow, Y is also approaching an arrow. That arrow is going in the left direction, so it's negative. It's also going down, which is also negative. And then on the right, we have this arrow. This arrow is going right, which is positive, and it's going up, which is negative, or positive, which is negative. There we go. Good. Go ahead and flip over the next page. Pause, try number 2, and then come back. Go ahead and check your box. The one that I think we might be showing on is this one right here. You can't see the x-intercept. I do know what happens though, because it's going up here towards our x-axis. It will take a while to get there, granted, but it will eventually get there. We just can't see it. We were given the y-intercept. Forgot to mark it. It's right there at 0, -5. The center I've marked. I also marked our concave up and down. That'd be right here. Remember, it swaps at the center. We are decreasing the entire time because it's going down. That's how we got to here. And then it exists forever from negative to positive infinity because it has arrows on both sides, which is also why we have no asymptotes, no restricted values, and no extrema. And there we go. Hope this helps. Bye.